In this video, we're going to take up one more problem on cantilever. The problem number 10. Find the reactions at the fixed end and draw the SFD and BMD for the cantilever shown in figure. The cantilever, one end is fixed and the other end is free. So here you have an UDL of 10 kilonewton per meter for a span of 2 meters from the fixed end A. Then at the point D, you have 40 kilonewton, which is acting from the upward or downward direction to the downward direction to get at a distance of 3 meters from point A. And similarly, at the point B, 20 kilonewton acting downwards, which is at a distance of 5 meters from the point A. Now, what we need to find, the first is we need to find the reactions at the fixed end. The reactions at the fixed end are, we have the horizontal reaction, the vertical reaction, and the reactive moment. So since all the loads are acting downwards, so the reactive moment will be in counterclockwise direction. So MA will be in counterclockwise. And all the loads are acting vertically downwards in order to keep the beam in the equilibrium condition. So that is the condition which we need to satisfy. So naturally, at RAV, you are going to have a vertical reaction acting upwards. And also we need to find out what will going to be the horizontal reactions on the beam. So first we are going to consider the reactions at the fixed end. So first is sigma h will be equal to 0. The sum of all the horizontal forces acting on the beam will be equal to 0. As there is no horizontal load acting on the beam, so as there is no horizontal load on the beam, therefore RAH will be equal to 0. Now we are going to take the sigma v is equal to 0. So the load acting upwards is positive. So that means that is the sign convention. RAV minus 10 into 2 minus 40 minus 20. So that will be the vertical load which is acting on the beam. So 10 into 2, it is because it is a UDL. So 10 kilonewton per meter. So for 2 meters, it will be 20. So 10 into 2. Then minus 40 kilonewton, which is at the point D, and minus 20, which is at the point B. So summing up all these things, and you're going to get the value of RAV equals 80 kilonewton. Now we are going to consider the sum of the moments acting on the beam will be equal to 0. So taking the moments about the point A, clockwise couple will be equal to counterclockwise couple, or in other words, the counterclockwise couple is negative and the clockwise couple is positive. So MA is the reactive moment, so naturally it should be a counterclockwise direction. So minus MA. So minus MA plus 10 into 2 by 2, because in the UDL it is 10 kilonewton per meter. So it means you have 2 meters. So the total load on the beam will be 10 kilonewton into 10 into 2. Then always the load acts at the midpoint for an UDL. So it will be 2 by 2 plus 10 into 2 by 2, 10 into 2 into 2 by 2, then plus 40 into 3 plus 20 into 5, which will be equal to 0. So MA will be, on simplification, you will going to get it as 240 kilonewton meter, which is in the counterclockwise direction. Now we will going to consider the shear force and bending moment for each segment or for each point. Now let us consider the first case wherein it is between D and B, where at the point B you have a 20 kilonewton which is acting. At the point D, we have not considered the 40 kilonewton. Without considering 40 kilonewton, what will going to be the load we will going to find out. The shear force at B will be equal to plus 20 kilonewton. The sign convention is considering the section. The load acting downward towards the right of the section will be positive. So that is plus 20 kilonewton. So between D and B, as there is no load acting on the beam, so naturally it remains constant. So between B and D, it is a constant at plus 20 kilonewton. So when you plot for the shear force diagram, you can see here at the point B, you have 20 kilonewton. Between B and D, it will going to remain constant, which will be 20 kilonewton positive. Now similarly, what will going to be the bending moment at the point B? So the bending moment at the point B will be equal to 0. And the bending moment at the point D will be, as the load is acting downwards, the beam will try to bend in the downward direction. So it will going to be hogging. So according to the sign convention, it will be negative. So minus 20 into 2 which will be equal to minus 40 kilonewton meter. So when you are plotting this, so BM bending moment at the point B will be equal to 0 and the bending moment at the point D will be equal to minus 40 kilonewton meter. Now we will going to consider a load on the beam, point load at the point D now, and also the distance between D and C. So we're going to consider till to this point. So you're going to have at the point B, you have 20 kilonewton, and at the point D, you have 40 kilonewton, and at the point C, you don't have any load there. So considering that, so now we will go for the shear force at shear force. First, we are going to consider what is the SF at D now. So SF at D, because SF at B will going to be 20, between B and D it is 20. So when the point load is applied at the point D, 40 kilonewton, so immediately it will go to be plus 20 plus 40, it will go to become plus 60 kilonewton. So that means at the point D, it will going to rises to 60 kilonewton. Between D and C, what happens? As there is no load acting on the beam, so naturally it remains constant at plus 60 kilonewton. So what is the SF at the point C now? SF at the point C will be equal to 60 kilonewton. So plus 20 plus 40 will be equal to plus 60 kilonewton. So as we see here, at the point D, when the load of 40 kilonewton is applied, so it will going to rise to 60 kilonewton. Between D and C, as there is no load, it remains constant at a distance of 60 kilonewton till to the 1 meter from D. So from here to here, you are going to have a constant of plus 60 kilonewton. Now we will going to consider the bending moment at the point C now. So that will be equal to minus 20 into 3 minus 40 into 1. So you will going to get it as minus 100 kilonewton meter. So this is how we are going to get at point B, it is 0, which is already taken. At the point D, which will go to be minus 40. And at the point C, you will going to get minus 100. All these points are joined by means of a linear line because it's a point load. Now we will going to consider the between C and A now. So SF at the point A. So SF at the point A will be plus 60 plus 10 into 2. It will going to become plus 80 kilonewton. So that means as you have an UDL, since it is a UDL, SF varies from plus 60 kilonewton to plus 80 kilonewton linearly because of UDL. So when you see that, you can see here up to point C, it remains constant because of 60 kilonewton between D and C, as there is no load acting on the beam. At the point C, it keeps on rising till to 80 kilonewton because of uniformly distributed load. So BM between C and A, SF varies linearly from plus 60 kilonewton to plus 80 kilonewton, which is as shown. Then we are going to find out what will going to be the bending moment at the point A. So the bending moment at the point A will be equal to minus 20 into 5, then minus 40 into 3, and minus 10 into 2 by 2, which will be equal to, on simplification, you will going to get it as minus 240 kilonewton meter. So because due to the UDL, it will go into further drops to minus 240 kilonewton. So that is how you will going to get from 40 kilonewton meter to 100, from 100 to it becomes 240. As we can see in the UDL, it is 10 into x into 10 into 2 into 2 by 2. So W into x by 2. So that will be equal to Wx square by 2. Since the power of x is 2, therefore you will going to get a parabolic curve. So the point joining between the point C to A, because C to A you have an UDL, so therefore in the shear force diagram you will going to get in the bending moment diagram you will going to get a parabolic curve. So that is the reason why we are joined between point C to point D by means point C to point A means of a parabolic curve. So this is how you will be able to get the final solution for a cantilever beam with number of loads as shown in the figure. Thank you.